So today we are going to do the repeat of lecture 1 with the Mimio device. Okay, so let's start with introducing the system of linear equations. What exactly is a system of linear equations? What exactly do we mean by a linear equation? Okay, so let's basically take an example of two equations. Something like, say, 3x is equal to 1, x plus 2y is equal to 3. So this we call as a system of linear equations. System because you have more than one equation. And the reason we call them as linear is the variables that are appearing in this equation, x and y, both are being raised to the first power. So the powers of x and y are less than or equal to 1. So for example, there is no y in the first equation, so the power of y is 0. And in the second equation, both x and y appear as with powers 1. Okay, now given this system of equations, we will introduce multiple ways of interpreting them. So there are two main ways we will focus on. One of them would be the geometrical way, or we will like to call it as the geometrical interpretation. The other thing is what we are more interested in is the so-called algebraic interpretation. So now when I say geometrical interpretation, why are we interested in that geometrical interpretation? Because ultimately what will happen is in lower dimensions like the two dimensions or 3 dimensions, we will be able to understand things because we can view them. And from there we will be able to get some algebraic interpretation out of it. As we move into higher dimensions, we will see that no longer our geometric intuition is helpful. And that is when we have to rely solely on algebraic methods. But the foundation from lower dimensions, which we will be able to visualize, will be able to help us do the algebra also. So let's come back to a simple question. When I say x is equal to 1, what exactly does this represent? So the question we are interested in is, what is represented by this particular equation? Now, when we first pose this question, x is equal to 1, depending on what level you are at, you might have different interpretation, and that is what we are more interested in, is to ask you exactly how do you interpret x is equal to 1. Does it represent a point? Does it represent a line? What does it actually represent? This is where we have to be now very careful. For example, if we are in one-dimensional situation, then x is equal to 1 will actually represent a point which marks the position on the real axis of the point we call as 1. If we are in 2 dimensions, the interpretation of the same equation will be slightly different. In 2 dimensions, when I say x is equal to 1, then basically what it is actually a line which passes through the point 1, 0. It's a vertical line which passes through the point 1, 0. So as you can see, depending on the dimensionality of this space, we have a different interpretation associated with the same equation. So when somebody says, oh, x is equal to 1 always represents a line, that's not an entirely true statement. In fact, if I go into 3rd dimension, then this x is equal to 1 will be representing a plane. So it's no longer a line, it's a collection of lines, if I may say so. So x is equal to 1, the best we can say is that it's a equation which represents a geometrical object, and depending on the dimensionality of the geometrical object, dimensionality of the space we live in. So for example, in 3 dimension, this plane is what we call as being represented by x is equal to 1, assuming that it's a horizontal plane. This is your x-axis, y-axis, and z-axis. Okay. So from now on, whenever somebody gives us an equation or a system of equations, we have to be very careful and ask ourselves what is the ambient space in which we are working. And based on that space, we will try to interpret the answer or the solution to that particular system of equations. Okay, so let's revisit this system again, and we'll try to understand what it means for us to solve an equation. And we will learn how to interpret them geometrically. What exactly does a system mean from the geometrical point of view? Okay. So let's come back to the same system we started with. Now, as you can see, there are 2 variables or 2 unknowns, x and y. So at least we know that we are working in a 2-dimensional space, or maybe a higher dimensional space. But let us focus for now that suppose we are working in the 2-dimensional space, which we will represent as R2. So 2-dimensional space. I'll add a word over here which may or may not mean anything right now. It's a 2-dimensional real Euclidean space. Real because we'll be dealing with real numbers as our scalars. Euclidean has something to do with the geometry of the space, and it will follow all the rules of Euclidean geometry. And we will try to interpret 3x is equal to 1 and x plus 2y equal to 3. So what does this system actually represent? So we were in a 2-dimensional setting in R2. Suppose this is my x, this is my y. This 3x is equal to 1, as we saw in the previous example when I was using x is equal to 1. This represents a line which passes through the point 1/3 0. So here is a line which passes through the point 1/3 0, and this is what equation 1 represents. So let me call this as equation for line L1. So this is my line L1. Now the second equation, being a linear equation, again represents a line. So let me call this as the line L2. And this is another straight line. We can try to plot this line. So for example, whatever this line might be, when I plug in y equal to 0, x is 3. So it cuts the x-axis at a point 3, 0. And when x is 0, y is 3/2. So it cuts the y-axis at say point 0, 3 by 2. I'm not drawing this to scale deliberately just to prove a point that we are only interested in a geometrical interpretation which can help us build or see into its algebraic interpretation. Now, when I say I want to solve the system of linear equation, that means I want a value for x and a value of y which satisfies both these equations. What it means is I want a point xy. So this is what solving means for us. We want a point xy that lies on both L1 and L2. So here is my line L2, here is my line L1, and I want a point which lies on both of them. So as you can see, from geometrical standpoint, it means we are interested in knowing the intersection point of this line. Of course, finding intersection point geometrically is also possible if we draw this drawing to the scale. Possibly we can, after some careful examination, we will be able to locate what that point is. But remember, I said I'm deliberately not drawing it to the scale because we want to find another way to find that point. And that is what we will call as our algebraic way of solving the system. So we need some kind of an algebra which can help us find that location, what that point is, which lies on both of them. And whatever that point might be, that would be the solution to our system. Okay. So let's try to give a shot at solving it, and then we'll try to understand more about lines in two-dimensional spaces or three-dimensional spaces. So the question is, how do I solve it? Well, one thing is clear, that the first equation forces that no matter what we do, x must be 1/3. Now from the geometry point of view also, you see the point that we are interested in, let me call this point as point P. The point we are interested in definitely has its x coordinate as 1/3. Now what we can do is we can take this value of x, plug it in my second equation, and try to solve for y. So if I do this from the second equation that I have, I will get 1/3 plus 2y is 3. So this would be y would turn out to be 4/3. Okay, so that means x 1/3, y 4/3 is the point that we are after, and this would be our common point which lies on both the lines. One thing is for sure, the coordinates of that point definitely satisfies the first equation, because the first equation just says x must be 1/3. And if you look at the second equation, plug in those points, we can justify that it also satisfies the second equation. So hence, we know that both these equations are satisfied with that particular point, and hence that was the solution we are looking for. Now, of course, we can feel happy that we have found a solution, but we should also at the same time ask ourselves, from geometry it seems that these two lines will intersect at only one point. Can such a thing be guaranteed from the algebra also? Well, if you look at the algebra, we knew that x is going to be 1/3, otherwise the first equation is not satisfied. And the moment you fix x to be 1/3, the value of y turns out to be a unique value, 4/3. So algebra also substantiates the fact that you are going to only have one solution. Now that raises a question: if I give you two straight lines or two equations like this, will it always result in one solution? Can it result in more than one solution? Could it be possible it has no solution? Could it be possible it has 23 solutions? So on and so forth. So these are the kind of questions we want to answer in lower dimensions first, and then we'll take it to higher dimensions. Okay. So let's try to see what our intuition or what our geometrical interpretation tells us in, let us say, in second dimension. What all possibilities can we have if I'm given a system of equations? Now, one thing worth mentioning here is, if we are living in two dimensions, it doesn't necessarily mean that system should have only two equations. System can have more than two equations, but each of the equations will represent a straight line for us. Okay. So let's again focus in two dimensions and see what all things can be said. Suppose I'm given two lines. Two lines basically for us mean two linear equations are given. For us. What are the possibilities? Well, let's try all possibilities that can come to mind. One of the possibilities is I was given two lines. So it could be something like this. So these are the two lines. As we can see, they only intersect at one point. So we can say this is a scenario which we just saw, and we have a unique solution or only one solution possible. Question is, if I am given two lines, is this the only possibility, or can it happen that they have no solution? No solution meaning what? They don't have a common point. And from geometrical ideas, we can definitely say if we are given two straight lines which are parallel, then definitely it has no solution. So parallel line and it has no common point and hence it has no solution. So it could happen that we are given two equations in a system. They both turn out to be representing parallel lines, different parallel lines, and we don't end up getting any solution whatsoever. Could it happen that there's more than one solution? So what if we are given two equations? They both represent the same straight line. So say something like this. They both represent the same straight line. So first equation represents this straight line. The second equation represents the same straight line. It's just that the equations are slightly different in the looks. Otherwise, they are representing the same geometrical object. In this case, we can see that every point which lies on the straight line is a solution. So in this case, we can say that it has infinitely many solutions. So we have seen three scenarios: a unique solution, no solution, and infinitely many solutions. From the geometry that we know in 2 dimensions, let us try to think, is it possible for two straight lines to intersect at just say 7 points? No less, no more, only 7 points. Well, you know, a straight line is completely determined if I give you 2 points. If I give you 2 points in a plane, then a unique straight line passes through those 2 points. Because the slope is fixed, one of the points you can use as a reference coordinate. So once two lines agree on 2 points, then can we say that those 2 lines will actually be the same line and they will agree at all their points? So that means if two lines intersect at 2 distinct points, then that means they will intersect at all the points which lie on the line. What does this mean for us? It means that if I am given 2 linear equations, and if I can somehow tell that it has more than one solution, then that means it will have infinitely many solutions in at least 2 dimensions. Will the same thing hold in 3 dimensions or higher dimensions? That is what we are after. And the surprising thing we will see is that whatever geometrical intuition we have in 2 dimensions or 3 dimensions, that gets carried on in higher dimensions, even when geometry seems to be slipping away from us. Okay, so in 3 dimensions, I'll give you some ideas to look at and see. We will have pretty much the same scenarios happening. So let us consider a system of equations in 3 dimensions. So again, we are given 2 equations in 3 dimensions, and in 3 dimensions, these linear equations will represent planes. Now, same kind of thing we can ask ourselves if we are given 2 planes. Suppose I give you 2 planes, one of them say looks like this, and another one looks like this. So if we are given 2 planes, as you can see, 2 planes may intersect at a line. So when 2 planes intersect at a line, then that means there are infinitely many points which are common to those 2 planes. So this could be a scenario for infinitely many solutions. Could it happen that I am given 2 planes and they don't intersect? Well, think of 2 parallel planes. To give you an example, look at the roof and the floor. The roof and the floor are 2 parallel planes which will never intersect, or at least hopefully they will never intersect. So this is what we call as scenario with no solution. So we have seen infinitely many solutions happening, we have seen no solution happening. Is it possible that I am given only 2 planes, 2 equations, and can they intersect at only one point? Suppose I only give you 2 planes, no more than that. If you think from the geometrical perspective, anytime 2 planes come to meet each other, it's like, think of a knife and a butter. The moment they come in contact, there are 2 planes intersecting, and whenever 2 planes intersect, then they will cut each other at a line. So you have only infinitely many solutions or no solution possibility. But what if I introduce a 3rd plane into the mix? What if I gave you 3 planes instead of just 2 planes? Can it happen that it has infinitely many solutions? Definitely it can happen that it still has infinitely many solutions. Just imagine these are 2 pages of the book. I attach one more page to this at the same spine. So these are 3 planes intersecting at a line, hence infinitely many solutions. Can it happen that we are given 3 planes and it has no solution? Why not? Like, just add one more parallel plane to it and it will have no solution. Would it happen that 3 planes intersect at only one point? So here is the question that we are interested in, just from the geometrical perspective. Can 3 planes intersect at only one point? Now if you think, maybe sometimes people say, oh no, it's not possible. But if you think a little bit, you will see that there is definitely a possibility. If you look around yourself, look at the corner of that room. There are 3 planes meeting at the point. So if you look at this as a wall, this as another wall, and this is your floor, then these are 3 planes which are intersecting and meeting at a point. So definitely 3 planes can intersect at only one point, and this would be a situation of having a unique solution. This brings us to an interesting point, that with 2 planes we had only these 2 possibilities, but with 3 planes we are having these 3 possibilities, the same kind of possibilities we had in 2 dimensions. Is it possible that 3 planes intersected, let us say 5 points? After a little bit of thought, you will be able to see that such a thing is not possible. So instead of going into geometrical interpretation, I would like to prove that using algebraic ways. So I'll postpone the proof for some time because we can have a proof which works in all dimensions. But at least from geometrical perspective, you can see these are the only 3 scenarios that can happen even in 3 dimensions. So of course, the natural question to ask is what happens in 4 dimensions when we have more degree of freedom to look at. Now, before we move on to higher dimensions, I have just one question to ask. When we were in 2 dimensions, we said no solution can happen if I am given 2 parallel lines. When we are in 3 dimensions, I again gave you an example of no solution when parallel planes are given. Is it possible to have 3 planes in 3 dimensions, of course, in R3, which neither of them are parallel to each other? That means no 2 of them are parallel to each other, and yet there is no solution. So this is something that you can think about. That is parallel condition the only way? Is it possible to have more than one way of having no solution? So 3 planes that are not parallel to each other pairwise, but still they don't have a common solution. Is it possible? You can think about it and play with some drawings and get some answers out of it. Okay. So let's try to continue our quest of solving system of linear equations. So we are now going to try to solve So let us consider this system x minus 2y equal to 3, 2x plus 3y is equal to 7. Okay. Of course, we can ask ourselves what space we are working in. Let us say we are working in 2 dimensions. So these are 2 straight lines. Now, if I write this same system, but suppose I give you different names to the variables. Can I say that these 2 systems are exactly the same except for the names of the variables that I've used? So the point is, these 2 represent some straight line. When you have marked your axis as x and y, these 2 equations also represent the straight line, the same straight lines which you had over here. And only thing difference is that instead of calling x and y, we are calling a and b. So name of the variables is not important at all when we are dealing with the solution to a system of equation. Okay, so that means these 2 systems are one and the same for us. Okay, so since the names are not important, we decide to drop the names. That means our main focus is only on the numbers or the coefficients associated with these variables. So what we do is we isolate the coefficients and we will only play with this so that we don't get mixed up with the variables or their names. So what we do is we create a matrix of the coefficients over here, and let me just put a bar over here. This bar basically tells that this is the left hand side of the equation, that is the right hand side of the equation, and we give this thing a name. We call this as an augmented matrix. Okay. So, in general, whenever we have a system of equations, we will be able to write it in terms of this augmented matrix. This left-hand side, we call this as the coefficient matrix. And this right-hand side we call as the right-hand side vector. For short, sometimes I will just call it the right-hand side or right side. So in general, we will use a notation for it. So this vertical line basically tells you the distinction between what is the coefficient matrix. So we generally write the coefficient matrix as matrix A, and the right-hand side we write it as a vector B. So this is the most common notation that we are going to use to represent a system of linear equations. Okay. Now, one thing I want to emphasize upon is, once again, the variables are not important. It's the coefficients we are interested in. Given a system, we can always convert it into an augmented matrix and try to play with this matrix. Of course, we still need to know how to play with this. But the fact that I want to emphasize is that if I give you an augmented matrix, suppose I give you a coefficient matrix and the right-hand side vector with a vertical line in between. If I give you an augmented matrix, then we will be able to look at this matrix, convert it back into the system of equations. Of course, we need to know the name of the variables. But the point is, this augmented matrix gives you the same system of equations as that means either you can say this one or that one, apart from the name of the variables, it is still referring to the same system of equations. So for each system, there is one augmented matrix, and for each augmented matrix, there is exactly one system of linear equations, barring the name of the variables. Okay? So from now on, whenever we are going to solve a system of equations, we are going to focus our attention on augmented matrix, and we'll see, or we'll try to see how to play with this augmented matrix from now on. Okay. Now before we learn to play with augmented matrix, there are two things that I would like to bring your attention to. And those two things, I like to call them as the row picture and the column picture. The reason I am bringing these two pictures right away is we want to have some kind of a way to understand the system of equations in more than one way. One of the ways, as you will see, we are more used to. So given a system, we sort of tend to favor one of these ways. But I want us to come out of our comfort zone so that we can start thinking in terms of the other picture also, because that other picture will be quite helpful later on when we go into higher dimensions or when we learn how to solve the system of equations. So first, let's get the easy task done. What the heck I mean by x minus 2, what do I mean by the row picture? So when I say row picture, it's the usual interpretation that we are interested in. So nothing new. What it means is I'm going to look at these two equations from the perspective of rows. So I will interpret them the way. Well, you will say, so what's the big deal? I already knew this. That is where my point is, that this is the usual thing that we like to do. And the row picture out here represents is basically two lines in a two-dimensional space. So nothing new, nothing fancy about it. If I was given 3 equations, it will be 3 lines in 2-dimensional space. Suppose I was given third variable, it would be planes in 3-dimensional space, so on and so forth. What about the column picture? If you look at this particular system, I could have written this system slightly differently also. For example, if you look at this vector 1, 2, if I scale it by x, and if you look at this vector -2, 3, and scale it by y, then if you look at the right hand side vector, it is 3, 7. So let's ask ourselves, can I not write the system of equation as that kind of an interpretation of 2 vectors scaled appropriately to give me the right hand side vector? If you look at this left hand side, this is nothing but, it is a linear combination. This word might be a little new for us, but we will have it so many times that after a while it will become second nature. It's a linear combination of 2 column vectors. So I'm assuming you are familiar with row vectors and column vectors from multivariable calculus. So it's a linear combination of 2 column vectors. So what does this tell me? It tells me one way to interpret this system is to think of it as intersection of 2 lines. The other way to interpret this system could be to see, can I scale these 2 vectors appropriately to produce the third vector? So can I take these 2 guys, combine them linearly and produce the right hand side? If yes, that means we have a solution to the system. One might still say, well, so what? What have I achieved? You might not be very impressed at this stage as to what you have achieved, but there is one thing that I would like to point out. Right now, we were in 2 dimensions, so this was a 2-dimensional picture. These 2 vectors also live in 2 dimensions, so it is still a 2-dimensional picture. But what if I had given you another variable just to have a fun, have some kind of fun? Let us say something like this. From the row point of view, we can say that this is basically intersection of 2 planes. So we are in 3 dimensions, and we are working with 2 planes and trying to find the intersection. But if you look from the column perspective, so from the column perspective, I can say that this is basically a linear combination of these 3 vectors. Now ask yourself, in which space do these 3 vectors live? As you can see, these vectors live in 2 dimensions. So that means the very same system which you were trying to solve, interpreting in 3 dimensions, can now be solved in 2 dimensions also. Or we can interpret it completely in 2 dimensions and try to solve it. I would agree, right now you may not see the utility of reducing the dimensions this way, but as we go along, you will see there is a reason why this thing will turn out to be useful for us, or it will help us interpret things quite nicely. Okay. Now, having said about the row picture and the column picture, I want to start looking into how to deal with this augmented matrix. I said, oh, let's play with it, but what exactly do I mean by playing with augmented matrix? Playing is a rather silly term. As you will see, we will have to make the augmented matrix work in a way we want. Okay. So now imagine if I was given, let us say I was still in R2. and I'm given a system of equations which looks like this. X is equal to 1, y is equal to 3. And I ask you to solve it. It may sound very silly, what do you mean solve it? It's already solved, x is 1 and y is 3. So you will say, well, there's nothing to solve, but let's pretend that we are going to solve it. What would be the augmented matrix corresponding to this? Let's just try to make an augmented matrix. X is 1, there is no y. There is no x here, y is 1. This is 1 and this is 3. Okay? Now, once we have got the augmented matrix, if you look at this augmented matrix, then can I say this augmented matrix corresponds to this system of equations? And as you can see, if such augmented matrix was given to me, then I would have had no problem interpreting the solution right away or reading the solution right away. I would say, oh, the first variable is equal to 1, the second variable equal to 3, and we are done. So in some sense, this is what we call as our dream augmented matrix. By the way, dream is not a technical term, it's just something I made up. So this is the so-called dream augmented matrix. If I can have such a matrix, or if I start with a system of equations and somehow I can convert that matrix into something which looks like this, then as you can see, solving will become very easy. So now the question is, if I start from any augmented matrix, let us say if I use this guy as an example, 1 minus 2, 3, 2, 3, 7. Question is, can we do something to realize or achieve a so-called the dream augmented matrix? That means, can we somehow do something which can lead us to a situation like this? Can we do this? If we can do this, then as you can see, we will be able to get our solution. So there are a couple of obstacles on our way. Question is, what do you mean by can you take this and convert it to that? We will call that as reducing the matrix. And the way we are going to achieve it is by doing something called row operations. That we will learn in the next lecture. What exactly are row operations? Once we have the row operations, or we understand what it means to do a row operation, we will reduce it to our dream augmented matrix, and we will have a name for it. We will call this guy as row reduced echelon form. The question is, if I am given an augmented matrix, can I do something called row operations to achieve something called a row reduced echelon form? Can I do it all the time? Or will I hit a snag sometimes? Sometimes I can do it, sometimes I can't. All these things we will study in the next lecture.